All right. The first topic I want us to take here is the section classification. There are a lot of stories before this, so you can just get the notes and read them up because theory also comes out in exam. I'll just be taking you through the calculation. So this is one topic, comes out in PQ, is your section classification. What this topic is mainly about is you taking a steel section and telling us if the section is plastic, if the section is compact, if the section is semi-compact, or if the section is slender. So the man mentioned to us that we have no business testing for slender. That once we have any value that tells us it's a slender steel section, then it is a failed section. So we will not be dealing with slender at all. We are going to focus on class 1, class 2, and class 3 steel. So how do I know something is a class 1 steel and class 2 steel or class 3 steel? It takes series of procedures. These procedures are very, very easy to get because we'll be making use of our BS codes for this calculation. So you are not really remembering any formula. All you are doing is that you are remembering steps to be taken. So they will give us a question. And in the question, what we do is that we use the dimensions, our BS code, our section table to get a value. It is that value that will now determine for us if our section is class 1, class 2, class 3, or class 4. Super easy to find. All right, so let's take a question. All right, so there's a question from past question. I think you also solved this particular one in class. We are told that a 457 by 171 by 67 UB. This 457 by 171 by 67, they are dimensions, Abi. Then UB means a universal beam. This UB is a universal beam. A universal beam is always I-shaped, like this. A universal beam is always I-shaped, this way. So there, you have your two flanges and you have your web here. Does that make sense? So the UB is an I-shaped beam with equal flanges. Sometimes these flanges can be unequal, but in this case, this RUB is going to be an I-shaped beam with equal flanges. So that's the interpretation to what we have here. So we are told that a 457 by 171 by 67 UB, so a universal beam, and we are given the steel grade. The steel grade is 7355. So we are going to be seeing that we have different steel grades. We have the 275, we have the 355, and what's the last one? I don't remember. So the steel grade is super important for any calculation that you are going to do. So you will note the steel grade. The steel grade is S355, right? So it's to be used under three conditions. We are told the three conditions. 1, when there is pure bending. 2, when there is bending plus the 700 kilonewton axial load. And 3, when there is pure axial load alone. What do you say we should do? Classify the section and evaluate the cross-sectional resistance. So once you see classify the section, it is under section classification. So as we've said earlier, the first thing to remember is that a universal beam is I-shaped. Then we are to remember the components of this universal beam. From the center of the beam to the end is what we call dimension B. Anyways, when you check your section table, you will see this drawing here, which might make it easy for you to remember. Then the capital T is the width of your flange, is the thickness of your flange here. Are we good? Then the small t is the thickness of your web. This long part is called the web. This place here is called the flange. Are we good? Then the big B is the width of the flange. Small d is the distance between the two flanges. Then big D is the distance from the top here. Just get familiar with these guys, because we are going to get our flange dimension. Our flange dimension is B over T, and our web dimension is D over T. Super important. We are going to be using this for calculations. I can call this my B over T X, and I can call this my D over T Y. Anything you want to call it. So after this, we are now going to start taking all our calculations step by step. Hope this part is clear. All right. So I think David has a clear stuff for our section table. So is this section table that you are going to be making use of. So in your section table, you are going to be looking for universal beams, UB. So this guy here is your universal beam. So in your universal beam, you look for your dimension. The dimension that we are given is 457 by 191. So you check. This is not clear. So this place here is 457 by 1. You will not even be seeing it. So in your section table, you have different stuffs: breadth of section, big B, depth of section, web of section, flange. You have all these things. You have your B over T, your D over T. Then you have your area of section also. I think the area of section is on this. Okay, on this side you have general stuffs like your radius of gyration, section modulus, your moment of inertia. Then I think area is somewhere here. So you are going to be getting these stuff. I've already written them down. You'll be getting your D from your section table, your B from your section table, your T from your section table, your thickness from your section table, your D from your section table. AG means area of section, is also on the section table. Your flange B over T is there, your web D over T is there. You are going to be getting all these guys from your section table. So once this information is clear, you are done with this. Then you are going to your BS code. This is all the information that you need from your section table. Once you get them, you are fine. All right, so after getting all these things from your section table, next thing you will do is go to your BS code. The problem here is actually realizing the next step to take. I think that's the main problem with steel, because it's a series of steps, and you can achieve this by constant practice. You can solve a question like 3-4 times. At least you get familiar with the steps. After getting the values from the section table, you need to go to your BS code. And your BS code, we are going to table 9. Table 9. In our table 9, what we are looking for in table 9 is the strength of the steel that we are going to use. So you look for table 9. I should have written that page. Okay, this table 14. This table 9 here. So table 9, you will see the design strength for your steel. So this design strength is dependent on the steel grade that you are given. If you look at your question, we are told that the steel grade is S355. So there is steel grade of 275, 355, and 460. We mentioned this earlier, Abi. So we are given S355. Now you go and check for the for the thickness of the steel. For the thickness of the steel, were we given what are we given in our question as our thickness? So you go and check this your T 12.7, and you go and check this your T 8.5. So you pick the largest one out of this 12.7 and 8.5. The 12.7 here is the largest. Pick this large one, 12.7. That will be your thickness. So you go back to your table 275. Look for thickness of 12.7. There's no thickness of 12.7 here. The least thickness we have is what? 16. Since there's no thickness of 12.5, you will use thickness of 16. So any thickness that is less than 16, you make use of thickness of 16. So the thickness of, so for example, if they give you thickness of 28, what thickness do you make use of? 40. They give you thickness of 45, what thickness do you make use of? 63. Thickness of 79, you make use of thickness of 80. Right? If it is less than 60, so from your table 9, we've now agreed is S355. We've gotten our thickness. Our thickness was less than 16. That means our design strength for our steel will be 355 Newton per millimeter square. So once you are done with this, you close your table 9. You are going to the next table. The next table we are looking for is table 11. So this table 9, table 10, and for our classification of cross section, we find table 11. Table 11 is giving us the width to thickness ratio of our different sections. For section classification, it is this table 11 that gives you your final answer. It's this table that you pay attention to. Are we good? This table. So the first thing you are going to calculate from this table is this your E, your parameter E. That's the first thing you calculate. The parameter E is square root of 275 over the design strength, Py. So you get your E to be 275 over Py raised to power 0.5. I'm getting 0.88. Very important. We are going to be playing around with this 0.88. Then we'll now get the class of the design from table 11. Now let's explain table 11. Table 11 gives you different sections for your compression elements, right? So remember, we are dealing with a UB, what do you call it, a universal beam here, and this universal beam has both flanges and webs. That means there are going to be two calculations, or right, there will be a design for your web and there will be a design for your flange. You are going to design for your web and you are also going to design for your flange. So let's start. You have to look out for on this column here, you have to start looking for your flange and look for your web. So what can we see in the first one? Outstand element of compression flange, road section, welded section, internal element of compression flange. This is not our business. Web of an IH or box section. So you can see that our what do you call it? Our beam was I-shaped, Abi. So this one talks about web of an I section. So we need this for our web, right? So for our web, we have two conditions: neutral axis at mid depth. Then if R1 is positive, R1 is negative, and axial compression. Don't worry, we are going to see this. Remember, in our question, the first thing they asked us to look for was what was that question again? Pure bending. Pure bending occurs when what do you call it? Your neutral axis is at your mid depth, is at the center. That means this first condition is what we are looking for. This neutral axis at mid depth is used for pure bending. Are we good? So we are giving our D over T ratio because it tells us that it's web. Remember, it tallies. Remember, we said for web, what do we use for web? D over T. We've called it Y. Good. So you go to your table. Under this D over T, you are seeing 80E under class 1 plastic. You are seeing 100E under class 2, which is compact. You are seeing 120E under class 3, which is semi-compact. There should be class 4 slender, but we've said that anything that exceeds compact is assumed to have failed for what we are learning here. So the first thing you do is to calculate your D over T. For web, what's our D over T again? Our D over T, we've calculated it. Where's our D over T? 48.0. Abi, as we said earlier, we are going to design for the web and we are going to design for the flange. For the web, we use our D over T. Our D over T is 48. Right? Let's just call this D over T X or Y. I think I called this Y earlier. It does not matter. For it to be a class 1 plastic, your D over T has to be less than 80E. If your D over T is greater than 80E but less than 100E, then it is class 2 and it is compact. But if your D over T is greater than 100E but less than 120E, it is class 3, which is semi-compact. If it is now greater than 120E, that means this particular design has failed. It is slender. So that means what we are going to calculate here is that we calculate our ATE. Abi? For our web, we calculate our ATE. Our ATE is giving us 7.4. And our D over T is 48. Is 48 less than 70.4? Yes. Since 48 is less than 70.4, that means it is a class 1. Please. It is class 1 plastic. It is class 1 plastic. Good. Then for your flange, you go through this table again and look for flange. Where is it? Oh, it's actually here. The outstand element of compression flange, then the internal element of compression flange is actually here. So it's the same thing. So we are looking for road section, welded section, compression due to bending, then axial compression. So we are using our road section here. The outstand element of a compression flange, our road section. So we are asked to calculate B over T. What's our B over T? We've calculated that that's our flange. Our B over T for flange is 7.48. So if 7.48 is less than 9E, it is a class 1 plastic. If 7.48 is greater than 9E but less than 10E, it is class 2, which is compact. If 7.48 is greater than 10E but less than 15E, it is semi-compact. So that's the calculation that we are going to do. So here 7.48 is, we calculated 9E is 7.92. 7.48 is actually less than 7.92. That means it is a class 1 and it is plastic. Same thing for your web, it is class 2. also plastic. So since the web and flange are both class 1 plastic, then the entire structure will be taken as the entire section will be taken as what? As class 1. What I'm saying here is that, for example, if I did the flange and I got class 2, and I did the web, I got class 1, I'm going to pick the smaller class as the design class of my whole section, right? If I got class 3 here and I got class 2 here, it means that for the design section, I will say it is a class 3 semi-compact. All right. The last one with pure axial load. Remember, we said the flange still designed as class 1. Abi? It's still plastic. So web, you now go to the web, go to your axial compression, calculate your D over T. So you can see that it is not a class 1 plastic, it is not compact either. They've given you not applicable here. That's why I said that's what's still confusing me. Why are we not using it for this? If you have an answer to that, please, we'll appreciate. I do not know why we are not using it for the flange. The man just said we should use the flange as road section, and we use this first one to test all true. But for this place here, they told us that class 1 plastic, there's no answer. Class 2 compact, no answer. So the only thing we can check for is this 120 over 1 plus 2R2. So you can see that Kini, for the axial compression and our axial load plus this thing is the same thing. Same. So you check 120E over 1 plus 2R2. What's that? 72.3. D over T is 48. 48 is less than this. So we design as class 3 semi-compact. So that means if this one is class 1, this is class 3, we design the entire thing as what? Class 3 semi-compact. So that's your section classification. It doesn't get more difficult than this, I believe. Amen. For the next condition, we are designing for the bending and the 700 kilonewton axial load. You know, we are giving 3 questions. And I already explained to you that your, your chart actually explains this. Neutral axis at mid depth. This one that the rule generally is for the bending plus load. This neutral axis at mid depth is for bending only. Then axial compression is for axial load only. Right? So now let's design for our flange. For our flange, what do we have? Our stand element of compression flange. We have road section and welded section, compression due to bending, blah blah blah. It's a road section actually. Yeah, this is explained in the whole theory stuff, but this particular flange is a road section. So we are going to be using road section throughout for this. We'll be using here. This explanation is not really clear to me, but this is what the man used in class. He used road section for all the categories. He used road section for question 1, pure bending. He used road section for design for bending plus 700 kilonewton axial load, and he used the road section for the axial load only. So this is what we'll be using for our flange, all true, right? So that means if you design, you are going to get the same thing. It is less than 9E because our B over T does not change. So that means our flange is still going to be a class 1 plastic. So I'm saying that your design for flange for this question 2 is going to be the same thing as your design for flange for question 1, which is class 1 plastic. But your web will change. Your web now move to web of an I or H box section. IH or box section. So this is the one that says axial load plus bending. We are seeing R1. Where is R1 coming from? No need to stress. Just move down to this place. R1 and R2 will be defined. The stress ratios R1 and R2 are defined in 3.5.5. So they are not things that you should cram. So you look for 3.5.5 here. 3.5.5 here. Defined. So we see that R1 is giving us FC over DT PYW, blah blah blah. So we know, check, how do I know what else FC is? Go here, they told you FC is the axial compression, D is our small d, the web depth. What else do we need again? T is our what? Web thickness, small t. What else do we need again? PYW is the design strength for the web. Design strength for the web, and that's all. So these are the values that we use to get our R1, then also get your R2. So there are no calculations that you need to cram or remember at all. So we'll calculate our R1, FC over DTPYW. We already know what these things are. So what's our axial compression? 700. We are given 700 kilonewton load over our small d. We've gotten our small d before from our table, 407.8. What else again? Our T, we know our thickness to be 8.5. Our small t is 8.5. Where is it? Here, 8.5 mm. Then, what else again? Our, what do you call it? Our design strength was 355. That's what we got earlier. That our design strength was 355. We got it from table 9. S355 was 355 Newton per millimeter square. So these are all the things you'll be checking from your table. No stress. So I'll calculate my R1. My R1 is 0.57. Calculate your R2 too. Your R2 is FC over AGPYW. Remember, we got this formula from our table. AG is area of section. We've gotten it before from the section table. We got area of section to be 85.5 centimeter square. You have to convert it to millimeter square. That's you multiply by 100. So that will give you 8550. 8550 times 10 raised to power 2. It will give you 8550. So use this formula to get your R2. R2 will give you 0.23. Once R1 is known, R1 is 0.57, R2 is 0.23. We go back to our table. What's that? Our table 11. Go back to table 11. All right. For table 11, what do we have for table 11? We are back to this second guy, this generally placed to calculate for our design class. So R1, what did we get? Positive or negative? Positive. We got R1 to be 0.57. So if R1 is negative, use this. If R1 is positive, use this. So D over T, what's our D over T? Blah, blah. We'll calculate it. You've calculated it. We know it. Condition 1. If D over T is less than ATE over 1 plus R1, it is class 1 plastic. But if D over T is greater than this and less than this, class 2 compact. If D over T is greater than this and less than this, class 3. So that means you must calculate ATE over 1 plus R1. So we'll calculate ATE over 1 plus R1. We got 44.84. What was D over T? 48. Is 48 where's that? Is 48 less than 44.84? No. D over T is greater than 44.84. That means it is not a class 1 plastic. We'll go and test for the second one. 100 E over 1 plus 1.5 R1. So you calculate that. 100 E over 1 plus 1.5 R1. It gave us 47.44. What was D over T again? D over T was 48. D over T is still greater than this. It is not a class 2 plastic. You go to the third condition. So what do you have? 72.33. So finally, D over T is less than this. Therefore, it is class 3 semi-compact. So we design our web as a class 3 semi-compact, and our flange is still taken as class 1 plastic, right? Remember, because we still treat it as a rolled section. But so remember what I explained. If flange is class 1 and web is class 3, what are we going to do? You pick the highest class, that's class 3. Highest class means the one that is lower, that's class 3. So everything is going to be taken as a class 3 semi-compact, just like that. So that's how you solve for the bending plus the axial load. The next thing we are moving to is our tension and compression. In our tension and compression, we always calculate for our compression capacity and our tension capacity. That's loads. They've given us a design load here, and after analysis, we are told that the compression member is 315.84 and the tension member is 115.18. I've not seen any question like this, but the only scary thing here is that they might give us a truss to analyze to get the compression and tension members. When we analyze it, we'll now pick the maximum members as our tension and compression. But I don't think the man has ever done something like that. Anyways, we are giving the compression member, we are giving the tension member. We will be giving the length of the member. The normal length of the member from node to node is 1.5 meters. So we'll be giving that. We are now told to design a section made of two unequal angles placed back to back and held together with a gusset plate. The important information here is that the unequal angles are not fixed, are not pinned. If they are pinned, alright, so we should design a section made up of two unequal angles placed back to back and held together with a gusset plate. I told you that this particular guy is not pinned here. If it is pinned, it is going to affect your effective length later. We are going to see that this plays an important role in our effective length. So we are giving the diameter of the bolt to be 20 millimeter. We are giving the class of the steel to be S355. You know what the class of steel tells us? It helps us to determine our our design strength with the diameter. Once our diameter is given as with the thickness that we are going to be given, it will help us to determine the design strength of our section. Now there is something about the dimensions of this section here. Sometimes we will be given, but many times we have to assume. The belief is that since you are a responsible engineer, you must be able to look at whatever you are trying to design and give a particular dimension for it. But anyways, the dimension here you are going to choose must be present in your section table. It has to be present in your section table. So this thing I wrote 75 by 100 by 10, you have to assume it. So our section table is going to be very, very important. In your section table, you are going to be looking for angles. This is universal beam. Okay, I think this is here. Here is equal angles. We are not using equal angles. We are told unequal angles. So we'll look for unequal angles. So this is the guy that we use here, unequal angles. So you can see that all these things here, their dimensions: 60 by 30, 75 by 50, 100 by 65, 100 by 75, 100 by 100, 90 by 90. If you are going to assume, anything you assume must be placed in this section table. It must be placed here. So the man assumed 75 by 100 by 10. You can always assume lesser. I think lesser is actually preferable. Maybe something like 65 by 100 might do the job, or 65 by 90. It does not really matter. Nobody knows. You have to design and find out if it is good at the end of the day, right? So once you've assumed this section, then work will start. All right, so what are the parameters that we have? We are giving the compression force, we are giving the tension, and we are giving the diameter of the bolt, and we are giving the class of the bolt. We have three classes of bolts: your 4.6, your 8.8, and the other one, I think we've shown it before. What this class of bolts will help us to do is to determine the clearance for our diameter. There must be a small clearance in the diameter of our bolt. So we are told to check table 34. You have to find a way to be very fast with checking the table. I'm still slow. Table 34, your bolt grade: 4.6, 8.8, and 10.9. Abi? Oh, don't mind me. Your bolt grade helps you to calculate your PY as if our tension strength, your PT. Please forgive me. We are going to check for that clearance later. So 4.6, our tension strength PT is 240. If it's 8.8, 560. If it's 10.9, 700. So we are giving our class to be 4.6. We are going to use it to check for our tension strength. Our PT is 240 Newton per millimeter square from the table. Right. Before we continue, the important thing is understanding what you are looking for here. What are you looking for in this place? We've been given the compressive load and the tensile load here. We are going to design our own section and also get a compressive load and a tensile load here. Then do a comparison to see if the section we've designed for is suitable. If the section we've designed for is not suitable, that means we have to pick another section. Oh, I didn't write this in the question. There is something that is always given, and that is your capacity over demand, C over D. There is a maximum value for it that is always given. Are we good? So if our answers does if our answer does not rhyme with this, we have to pick another section to design for. It will make more sense later. So at the end of the day, you are looking for a new compressive force and a new tensile force. Let's just see that come into play. We've gotten our tension strength, which is what? PT to be 240 Newton per millimeter square. So we'll now go to the next table, table 36. Please note it down. What we are looking for, table 36, is the clearance for our of the bolts of our diameters. We are giving the diameter bolt to be 20. So table 36 gives us the standard dimensions of holes of preloaded bolts. If the diameter is 20 mm, what's our clearance? We should use 22. So that diameter that we are giving as 20 is something you can actually memorize. So if you are giving it, you don't have to start checking your table, but please always check your table, sure. So diameter of bolts is 20. That means our clearance will be an additional to which is 22 mm. So we've gotten our tension strength, we've gotten our our diameter. Next thing now is to play around with your section table. In your section table, you want to get two things from your section table: area and moment of inertia. Once you get your area and moment of inertia, you are done with your section table. In your section table, remember, you are using unequal angles, right? So you go and look for your dimension. We chose 100 by 75. 100 by 75. So you now see three other values here: 12, 10, and 18. We chose our height to be 10. So go and look for area. Our area of section is 16.6. Where is it? 100 by 75. Our area of section is 19 under 10, 16.6. When you are done, go and look for moment of inertia. Moment of inertia is radius of gyration, is this guy here. When you look for radius of gyration, you're having 3.12 and 2.16. Once you found them, you can leave this place here. Your area of section, radius of gyration. So what's our area of section? We got 16.6. You multiply by 100 to convert to millimeter square. Since we have two unequal angles that are placed back to back, we have to multiply our area by 2. Our area now gives us 3320 millimeter square. Moment of inertia along the x-axis from the table, we got 3.12 centimeter. Convert to meter, that's multiplied by 10. Gamma y is 2.16 multiplied by 10, get 21.6. So out of these two moments of inertia, you have to design for the section that will fail first, because moment of inertia is the ability of the body to resist angular momentum, to resist the turning effect. So you pick the lower one instead of picking the higher. Radius of gyration, please, is not moment of inertia, radius of gyration. You will pick the lower one, the smaller one. You are designing for the part that will fail faster. So I will design for 21.6. Why am I getting gamma, radius of gyration? It is because of something we are going to use later called slenderness ratio. So as you are getting your gamma, the step is already coming into your mind. I'm getting gamma, so I'll find slenderness ratio. Because nobody will give you all these steps in exam. You are the one that will be picking it up. After you've gotten gamma, what's the next thing to do? As I'm thinking of gamma, I'm thinking of slenderness ratio. As I'm thinking of slenderness ratio, I'm thinking of effective length. So after this, my next step will be to calculate effective length. Effective length can be gotten from table 22, right? But I already explained this. Remember, I told you that here in our question, it was not mentioned that these guys were pinned. Are we good? If these guys are pinned, our effective length LE will become 1.0 L. But since it is held with a gusset blah blah blah, our LE becomes 0.85 L. You can see this information on table 22, which is on page 79. So you can see it, the nominal effective length for compression member. So if it is effectively restrained in both directions, 0.7 L. If it is partially restrained in direction at both ends, that's 0.85 L. That's how it is here. If it is not restrained in direction, that's we use 1.0 L. Anyways, we are using 0.85 L for this, for our effective length. So once we calculate our effective length, then we are good to go. So calculate your effective length, 0.85 times L. We are giving the L in the question as 1.5 meter, which is 1,500 mm. You get 1275. Remember, I told you are calculating your gamma so you can calculate slenderness ratio. Your formula for slenderness ratio is LE over gamma. You've gotten effective length 1275. You have gamma already. The smallest radius of gyration 21.6. You get this. After you are done, we go to a new table to complete our calculation. All right. So after you get your slenderness ratio, remember our PY, we get our PY from table 9. This is what we should all be familiar with now. Your table 9 will give you your design strength. So where's our table 9 again? Go to table 9, look for your grid and your design strength. Table 9, we had our S355 and our thickness, we assumed 100 by 75 by 10. So our thickness is 10, it's still less than 16. That means our design strength is still going to be 355. Remember that. So our design strength is 355 Newton per millimeter square. Now we are going to calculate, use our shortcut curve allocation to get to get our PC. Remember, from the beginning we've explained that the aim of all these things will be to design a section, and in this section we'll be getting our compressive load and our tension load. We will do some form of comparison using these two guys to see if our section is suitable, right? So what do we do here now? We are going to open to table 23, check our short curve allocation to be able to calculate our PC. So we'll go to table 23. In table 23, all we are going to have here is that we have three options to choose between A, B, and C, right? So we are going to look at this here. They've told us hot form structural hollow section. That's not our business. Blah blah blah. I'm looking for the guy I want. Rolled angle, channel or T section, two rolled sections, laced, battened, or back to back. So that's the one we are using. We are using our back to back. And in our back to back, we are told that any axis that we are dealing with, choose C. Any axis that we are dealing with, choose C. So you go to your table. This table is still saying A, and this table is saying C. So you can see that this table, there are different values of lambda. So in our question, what was our slenderness ratio again? Our lambda was 59.08. So you search for 59.08. We can't see it. We are seeing between 58 and 60. That means we have to interpolate. 58 and 60. What are you looking for? You are looking for S355. S355. Where is S355? Here. So between 58 and 60. That means you are interpolating between 247 and 252. So we interpolate to get that answer. What would this thing give us? It will give us our steel grade small PY. It will give you our small PC. Forgive me. It will give us our small PC. So good. We are going to interpolate. How do we interpolate now? Remember how to interpolate. Interpolation. We are interpolating between 59 and 60. So we are looking for 50. What are we looking for again? 59.08. 59.08. I can just call that 59.1. So 59.1. Wow, that's actually not between 50 and 60. Yeah, it's between 58 and 60. So I'm interpolating between 58 and 60. So what would that be? 60 minus 58 over 59.1 minus 58 equal to. So you go to 60 and trace for the value of 60. The value of 60 is 247. That's 247. Oh, please. Sorry, I got this interpolation wrong. So I'm interpolating between 60 and 58, and the value I'm looking for is 59.1. So I will have 60 minus the value I'm looking for, 59.1, over the value I'm looking for minus the lower boundary, 58. Very easy. 60 minus the value you are looking for over the value you are looking for minus 58 equal to, trace the value of 60, you get 247. The value of 59.1 we don't know. The value of 59.1 we don't know. Minus the value of 58. If you look at your table, the value of 58 is 252. 252 minus 252. So your aim here will be to solve this guy and find x. Right, good. So as we found x now, as I interpolated, I got my this thing to be 249.425. 249.425. So that means our capacity for P is 249 point, what do you call it? 0.25 Newton per millimeter square. Not our capacity, our small PC. Now we will calculate the capacity of the section. This is what we are looking for, our big PC. So this formula we have is, it is the compressive strength, right? That's what we have here. This PC, this compressive strength times the area of section. The compressive strength times the area of section. Compressive strength we have is 249.425. Area of section from the very beginning has been 3320. So our answer is 828.09. This is what we have been looking for. Once you get this, you will now go and check, what is my capacity over demand? My capacity over demand is the PC we've designed for, which is 828.09, plus the compressive distance they've given us in the question, which is 315.84. So I'm going to do 828.09 over 314.84, and I'm getting 2.6. It means that this section I've chosen is not suitable. I have to design for another section, because the capacity over demand always gives is 1.15. It should not exceed this, and we are having 2.6. All right, so we've calculated for the tension, for the compression PC. We are going to calculate for the tension now. To calculate this is very simple. You need to get your section area. What's our section area again? We got it from our section table, Abi, which was 1660. Then we multiplied by 2. Which is 3,320 millimeters square. Now we are going to get the area of our bolt holes. Why do we want to get them? Because we want to get the net area. And to get the net area, we have to remove that missing area there. We have to remove the missing area, and there will be 2 bolt holes here. Are we good? So the formula for the area of our bolt holes will be the diameter of our bolt, Abi, which is at 20, with a clearance that we've gotten from our table. Remember that clearance that we got from our table that gave us 22. For diameter 20, our clearance was what? 22. So it will be diameter times thickness times 2. Why are we multiplying by 2? Because we have 2 of them here. So diameter is 22. The thickness we assumed was 10. 100 by 75 by 10. Then multiply by 2. So we have 440 millimeters square. We can now calculate the net area. The net area is going to be the section area minus the area of the bolt holes, Abi. So which is 3320 minus 440. So the net area is going to be 2,880 millimeters square. After you've gotten net area, then there's one more area that we're meant to calculate. That is the effective area. Are we good? So to calculate the effective area, we use what do you call it? A table. We use our code section 3.4.3, but it's a formula that I can remember. Your effective area is KEAN. KE is actually what do you call it? Is a constant that varies. It depends on what you are given. So let's look at the table so you can see the values of your KE. So depending on the steel grade, it could be 1.1, it could be 1.2. So 3.4.3. So effective area AE is KEAN. Are we good? So for grade S275, KE is 1.2. For grade S355, KE is 1.1. So we are using grade SE355. Our KE will be 1.1. So KE, AE is equals to KE times AN. AN is the net area that we just calculated. So we get our AE to be 1.1 times 2880, which is 3168 millimeter square. Are we good? So now, since this our section is not connected to any bolt, we are going to use this formula for our PT. Our PT is what do you call it? Our tension capacity. Our tension capacity will now be our net area, not our effective area,